Okay, and welcome to 10B, where we're going to talk mostly about the life cycle of stars. And if you can see here, we're going to talk about the Hertzsprung-Russell diagram. And these are two German, I think Swedish scientists that at the same time started to look at stars and realized that all stars shared two things. And these two things are, if you look at this diagram right here, are the true brightness, which is absolute magnitude, and we're saying that 0 is located up here, and we're saying that +5 is down about where the sun is, and the larger the number, the dimmer the star. And that also ties to the luminosity of the sun, where we can see 1, we're talking about solar looms, and then we'll go up to here, these are 10 to the 10th, which is 100, and then 10 to the 4th, which is 10,000, and then we go 10 to the 6th, which is a million times brighter than the sun, or we can almost go a million times dimmer than the sun. And then they also share surface temperature. And you can see stars go from a little bit under 3,000 K all the way up to over 40,000 K. It's also known as the spectral type, where we actually talked about Oh Be a Fine Girl, Kiss Me, and the O stars being the really hot stars, and the M stars being the really cool stars. And you see they go from 0 to 10. Actually moving down this direction, the smaller the number in the letter, the brighter or the hotter the star would be. Here's another HR diagram, and actually I'm not sure where. There's supposed to be a little bear right here because I want you to draw this. And so go ahead and pause it because I'm going to move to the next one. But I want you to pay attention to luminosity, surface temperature, apparent magnitude, spectral type, and then the basic position of the three types of stars, which are located there along this red line, and then up in this area. Okay, so here's where we're going to give them names. These are called the main sequence stars, and you can see that the sun is located right there. Sun is located almost at about 5,800 K, and we are a G2 star. And you can see white dwarfs are in this area. They tend to be relatively not bright, relatively dim, because their luminosities are way down here. And they also tend to be really warm because they're basically from our sun temperature all the way up to some of the same things as these blue giants that are up here. And these are the blue giants. Here are the red giants, and then we have what are called supergiants, and the stars that are located up here, really bright. Here are two of the brightest stars you can see with your eyes. Deneb is actually the bright star in Cygnus the Swan, and Rigel is the second brightest star in Orion, but these are two of the biggest, truest, brightest stars you can see with your eyes. They are not the biggest, brightest stars that we've discovered, but they are the ones that you can see with your eyes. In fact, I think every star that you can see in here, you can actually make out with your eyes. Ross and Gliese and Wolf and Proxima Centauri, the Barnard star, these tend to be relatively close to us. They tend to be relatively small. And then some of these other ones we found when we found the October stars, and I didn't do the January. Maybe I should do the March stars, and you'll get some of the rest of these. Okay, here's the main sequence, and if you take a look at it, it almost looks like they're little dots on all these. And we start with the red stars at this end, we start with the white stars over there, we start with the dim stars on this end, and we start with the bright stars on this end. So we got brights up here, dims down here, and we have this main sequence that goes from the dim, cool stars all the way up to the hot, bright stars. So true brightness of the stars, or M, is plotted against the star spectral types. Brightness and spectral types are related. Main sequence stars, which are fusing hydrogen, make up most of the stars in the HR diagram, and they're changing hydrogen into helium, losing a little bit of mass, and E is equal to mc squared, producing a bunch of energy, and they follow along that red curve. And then giants are in the upper level. They're located up here. These supergiants at the top, these are actually using hydrogen. The hydrogen now is used up, and now they're actually using helium for fusion, and the fusion of helium produces a lot more heat, so it expands through stellar equilibrium, expands the star to a much larger size. And then the white dwarfs down here, These are below the main sequence, and the fusion is basically gone, and they're not fusing anything, and they're just basically going to cool and change all the colors all the way down to red dwarfs, and then finally down to brown dwarfs and maybe even black dwarfs. Okay, here's another bear. I'd like you to draw this square, and if you take a look, we've got lumens of the sun. So we've got the sun located along this one, and then 100, 10,000, a million times brighter, and then 100 times dimmer, 10,000 times dimmer, and a million times dimmer, and then again from a little less than 3,000, they're saying 2,500 all the way to 40,000 and above. So what kind of stars are located up here? Well, first we got to talk about what happens to temperature as we go this direction, and it does get hotter. And then if we go this way, it gets colder, so toward the brown. And then if we go this way, stars get brighter. And if we go this way, they get darker. And then what does that make these stars up here? Well, they're going to be off on this end, so they're going to be relatively warm, and they're going to be up here, so they're going to be bright. So these are hot, bright stars. Stars over here, they're located over in this direction, which is the cool temperatures, but they're still over here at high lums. These are going to be cool, bright stars. Stars down here, they're actually not very bright, and they're also not very warm. Cool, dim stars. And the stars over here, a lot warmer, not much brighter. And how do you make a hot star as bright as a cool star? They've got to be much, much, much smaller. So these are the white dwarfs, remember. And then what star is this one right along one lume? Sitting right around 5,800 K. That is, of course, our sun. And again, I'd like you to draw that. Star size is also important. Hotter stars are brighter than cooler stars, as long as they're the same temperature. Bigger stars are brighter than smaller stars, again, as long as they are the same temperature. So brighter stars are our biggest, hottest stars out there. And that all applies to this equation I gave you in the vocab, where luminosity is equal to the radius of the star squared times the temperature of the star to the fourth power. And I can't show you these because they're two YouTube videos, but I'll show those as well as those shock waves that were up a couple of slides ago. I'll show those to you in class. So mass, temperature, brightness. If you take a look at this, these are the main sequence stars, and they've got numbers by them. The dots actually show mass, so the mass of 1, which is what we're using for our 1, the stars up here are more massive, and you can see they actually get to be 3, 4, 5, even 60 times more massive than the sun, and then the ones down here actually get to be about 20% of the mass of the sun. So mass, brightness, and temperature of the main sequence star increases from the lower, so mass, brightness, and temperature. This is the coolest, dimmest, least mass star, increases going up this direction, so up and to the left. And these are the brightest, the warmest, and the most massive of all the stars. So all stars that are out there begin with nebula. This is the Rosette Nebula. It's also known as NGC 2237, or the National Galactic Catalog number 2237. It is 5,200 light years away from us, and it has a diameter from one side to the other of about 130 light years. This is actually as big as the Milky Way across it, and this is just going to become a star. And then every once in a while we look at this nebula and we see this weird object look like it's coming out of it. Or more like that's not really true. Okay, life cycle of the stars. If we have low mass stars, we can, in the main sequence, and if you take a look at it, we're talking about 0.05, so that's 8% of the sun, all the way up to 10 solar masses. They spend 90% of their lifetime here in the main sequence, and this is like the sun and a star called Altair. And the same thing up here, we still spend 90% of our lifetime, but our lifetime's not going to last near as long because we're fusing a lot more hydrogen to make this warm temperature. We're now 10 to 150 solar masses, and this is like Spica and Theta Orionis, and these are comparing 98% hydrogen helium stars, and 1/3 of the hydrogen is converted into helium. Okay, and then if we go, we'll do the high mass stars first. We go out to it, and what's going to happen is the hydrogen will run out, and we're going to lose some of the mass. And this is 10% of the life cycle, and this is where we actually get an expanding star. And this is Betelgeuse and Rigel. And then we go supernova because we're going to start fusing even more heavy atoms, producing much more energy. So that solar equilibrium is going to expand, but it will no longer be able to contain it due to gravity. About 10% of the original mass is ejected out in space. This lasts seconds. So this explosion is really, really, really fast. And this is like Cassiopeia A and Kepler supernova. And if you're not as big, 3 solar masses or larger, you'll go this direction. You can spend a lot of years this way. And this is a neutron star. And we'll talk about neutron stars in a little later. And if you have a lot more mass, like over here, I'm sorry, this is the black hole, where you have 3 solar masses or larger inside this black hole. Or if you have 1.4 to 3 solar masses, you become this. And black holes we'll talk about later. And then if you have low mass stars, you're going to do the same thing. You're going to run out of hydrogen eventually. You're going to start fusing helium, and this star will start to expand because of higher temperatures and stellar equilibrium. It'll actually produce what's called a planetary nebula, and then what will be left is this white dwarf. This star is typically composed of carbon and oxygen, which is the only thing our stars can create, where these massive stars can create everything in the periodic table. And when we actually say we are children of stars, we're not children of normal low mass stars. We're children of high mass stars and supernova. So if you take a look, it actually talks about life cycle. Incredibly long as a white dwarf, and then all this white dwarf can do is cool off and become a black dwarf, running through all the colors. Okay, here's another way of looking at it. Really massive stars, really low mass stars, and some stars like the sun, and there are some stars that actually form into red dwarfs, and then there are stars that form just into brown dwarfs, and they go this direction rather than going the white dwarf and slower down. Excuse me. So 3 types of really funky stars. First one is called a neutron star, and the first thing we have to know is these stars are actually about city size. So here's a white dwarf, here's the Earth, they're about the same size. So this is the remnant of our sun after the red dwarf planetary nebula has gone out. This is the size of a neutron star. If we could zoom in on it, it would look something like this. And it's created by giant stars, 1.5 solar masses or above. And it's after the after the supernova actually kicks out, just like this white dwarf is left for our sun. If you're a larger mass star, you actually end up with what's called a neutron star. And the collapsed core actually allows protons and electrons to sort of melt away, and it's left with neutrons. And to give you some idea how dense this material is, if you could get a teaspoon of it, which they're saying is 5 milliliters, the material would have a mass of over 5.5 times 10 to the 12th kilograms. And to put that into perspective, that teaspoon would weigh 6 billion tons. And you wouldn't be able to hold it on a teaspoon. You wouldn't be able to put it on the Earth because it would literally go to the Earth and go straight through, pop out the other side, and just keep doing this over and over and over and over and over as the Earth rotated around, and it would cause like Swiss Earth with a whole bunch of holes punched through it. Then we have what are called pulsars. Pulsars are rapidly rotating neutron stars, and they actually produce electromagnetic radiation in the radio area. So they actually look like lighthouses, except that these things pulse on and off thousands of times per second. Here's a GIF of a pulsar. You can see it spinning, not spinning, it's spinning faster than a lighthouse, but nowhere near a couple thousand pulses per second. And the pulsar is high magnetized, rotating neutron star, or sometimes a white dwarf that emits a beam of electromagnetic radiation. And one example of it here is this pulsar that's in this accretion disk. In other words, it's got still material around it, and it's really close to Swift J 1749, which is a K-type star, about 70% of the sun's mass and 60% of the sun's size. So this pulsar is actually pretty close. They're saying it's 1.2 million miles away. And then the last thing, and probably the coolest thing, is black hole. This is Cygnus A1. This was the first black hole material that we think we actually found, and what you've got is a black hole. And what this thing is actually doing is pulling mass off of this blue giant that's over here, which is Cygnus A. And it's actually pulling that material around, and we can see it spiraling in to basically nothing. And then what we see are X-rays that are being pushed out as this material is screaming due to friction as it's getting pulled into this singularity. So black hole is where gravity itself is so strong that not even light can escape. It's strong because the matter is squeezed together in a tiny space. So as dense as a neutron star, this is exponentially even more dense. Because no light can get out, these are not seen by visible light, which is where they get the name black hole, and they're invisible to most electromagnetic radiation. Space telescopes with special tools can actually see these by looking at these beams of X-rays that come around. We can also see it because of radio waves that are being produced and higher energy waves as this stuff spirals in. This is a video, again, I can't show you, can't embed it in this video because I'll get a copyright infringement. What we actually can see it, we can see it with what are called gravity waves. The singularity is located right here. That's the point where if you fell in, there's no way out. But the gravity of this actually bends light from stars that are behind it, and they start getting this wavy type version. And then here are two black holes that are animationally shown to collide. And it looks like they've already done it. Okay, here we go. And you can see the gravity wave that's behind it. It actually is changing the shape and the position and the motion of all these stars. So we can actually see these black holes through what they do to the background. And then what do you think? How near is the closest star to our sun? It is Proxima Centauri, 4.24 light years away. About 40 trillion kilometers, 25 trillion miles away. It takes light about 4.242 years to reach the Earth from there. How luminous is the sun compared to other stars? The most luminous stars are about 10 million times brighter, and the least ones are about 100,000 times dimmer. So we are somewhere right in the middle. What color are stars? Stars are found in a wide variety of colors, from red all the way through violet, as well as even blue, white, hot. Are brighter stars hotter than dimmer stars? Not necessarily, because remember, if you have a really small star that's hot, it may not be as bright as a cooler star that's larger. So many bright stars, such as red giants, are cooler but larger than hotter, dimmer stars such as white dwarfs. And what sizes are stars? Stars range from 1,000 times the sun's diameter to less than 100 times the sun's diameter. So they can get really big or really small. Are most stars isolated from other stars as the sun is, like one star? No. In the vicinity of our sun, 80% of the stars are actually found in binaries, or even larger groups. Binary means two stars orbiting, and here are 4 examples of stars. These two are actually showing you stars of similar mass with a central barycenter. That's the gravity point. Here are 2 stars in the same orbit, and as long as they are the same mass and they're revolving around, they should never touch each other, again around the barycenter. Here are 2 stars with different masses. The larger one is closer in. It could actually work the other way as well, but again, it's speed. And then here are 2 stars with one much larger, and this is very similar to the Earth Moon, where the barycenter is actually inside one of the stars. So that central rotation point is inside the larger of the 2 stars, like it is in the Earth, where it's even a little closer to the center with the smaller star orbiting around. And that's it. That is 10B. Thank you much. Bye.